This is a demonstration of an architecture-led requirement specification capability. It is a textual notation based on the RDAL draft annex that allows you to associate requirement specifications with AADL models. Before we get into notation, let me give you some motivation behind this notation. One of the things we have is some data about the quality of requirements. As we have textual requirement specifications, statistics from NIST and others show that requirement quality is in the form of 21% incomplete requirements, 33% missing requirements, and 24% incorrect requirements. There's a great opportunity for high payoff improvements by simply improving the quality of requirements in terms of coverage. Similar data shows that there is great uncertainty in requirement changes. Rolls-Royce, for example, has identified that 80% of requirement changes come from the developer team instead of stakeholders. Therefore, it is useful to be aware of where there is variability in the requirements. Some of them are driven by issues like volatility, precedence in the sense of first time performing a certain kind of system. At the same time, we also have inherent variability that we can engineer for by dealing with ranges of values in a requirement specification instead of a single value. As a result, they have been able to show a 50% improvement in requirement changes. Another view of the same problem space is illustrated here. It is based on a University of Minnesota study. Here is a set of requirement statements written in the same section of a document. Once we map that representation into an architecture model, we realize that we are talking about 4 different layers within the architecture. So effectively, we have partially specified an architecture of a particular system. It also makes us aware as to what the boundary of the system is for which we are intending to specify our requirements. In order to deal with the coverage, we have identified 3 dimensions in which we can focus on assessing whether we have enough requirements about our system. One is looking at the interface and the behavioral specification of the system. All interactions with other system components or the operational context need to be taken into account. Inputs map to output over behavior and state, making use of resources and being under some supervisory control. All of those elements effectively need to have requirements specified. So for example, if you have a system like a situational awareness system, we identify all the entities that need to be observed in order to create a common operational picture from a situational awareness perspective. Therefore, we need to have requirements about each of those elements. Not only do we focus on the functionality and the interaction points, we also need to deal with design and especially operational quality attributes. There we are making use of a utility tree notation that comes with the architecture trade-off analysis method called ATAM. And it also illustrates how we can take requirements and make them concrete enough that they become verifiable, which is a process of improving the ambiguity of systems, or by actually reducing their ambiguity of systems. And finally, we need to bring safety into the picture. For that purpose, we can utilize a fault ontology that comes with the error model Annex version 2 of the ADL standard suite. And as we map those onto an architectural structure, we can systematically identify potential hazard sources. That mapping shown at the bottom right is very much like a mapping that Nancy Levison is promoting as part of her STPA method for control feedback loop type of systems. One of the reasons we want to do this requirement specification is by first of all associating it with models, complementing it with hazards, and from that coming up with derived requirements to address these hazards. Not only that, we also want to associate verification plans, namely verification activities that we will perform to demonstrate that requirements are being met by implementations of the system, whether expressed in models architectural models, detailed design, or code. And as we do that throughout the whole system in an incremental fashion, we effectively over time build up the assurance case, namely the collection of evidence that at any point in time we know how much has been verified, we know which verifications fail, and we also are discovering issues early in the process. This work is being done under a project called Alisa, or Architecture-Led Incremental Lifecycle Assurance, with a workbench that is in development. The requirement specification notation that we are discussing here is one piece of that framework, but is also available standalone. One aspect of requirement specification is to say, well, we have AADL models. Here's an example of one, and we annotate the AADL model itself with properties. So we can then have various kinds of characteristics about the system that we expect to be implemented. So this system specification in some respects already acts as a requirement specification. One can then introduce specific additional properties to deal with the problem space. Here I'm illustrating some when processing requirement documents, namely dealing with aliases, namely different terms for the same object, new characteristics about the domain, such as observation radius and so on. So we will make use of properties in that context as well. But to deal with requirement specification, we don't necessarily want to embed all of that inside an architecture model, because it's really an architecture specification. When doing requirement specification, there are really two spaces. One is stakeholder requirements, or goals, as we call them in this slide here. We use that term based on the work on goal-oriented requirement specification. We developed a description for that includes description, rationale for the goals, traceability to stakeholders and other documents, and the ability to talk about refinement of goals, evolution of goals over time, and identifying conflicts between goals that need to be resolved as we turn them into system specifications. As we have them, we can organize the goals in a document-focused organization, the way you usually find them in documents produced in Word, namely document sections and requirements below. Or we can start taking an architectural view, which will be elaborated more when we talk about requirements as well, where we already are using a model of the system in its operational context to characterize issues and goals around the system. Here is an illustration of stakeholder goals. At the top, we show you how we organize that in terms of documents containing sections and inside goals with identifications, descriptions, and so on. At the bottom, we have an illustration of a set of stakeholder goals centered around a particular system, in this particular case identified with the for clause pointing to an ASSA sensor. Let us illustrate the requirement specification capability as a plugin to OSATE. Here we see OSATE opened up, and we see on the left-hand side the navigation view with a folder called RecSpec. RecSpec is also the name of the notation that we use. With that, you can create files with different extensions. There is the extension goal.doc to reflect that it contains stakeholder goals in document format, or goals to reflect the fact that it contains goals and centered around individual system specifications. Similarly, for requirements, we have RecSpec for requirement specifications around architectural elements, and RecDoc to have requirements organized in document format. When we have existing requirement documents for stakeholders, for example, that may exist in Word format, we can leave them there and then create requirements and point to those existing documents, or we can import those documents into our framework, and once we have them imported, they become available for traceability and analysis. Here we are opening a document that was imported from a Word format in table format, or in equivalent form from the RecIF interchange format. So it is organized in sections according to the original documentation, has a description of the different goals with the number labeling that was in the original document, and assignment of a particular stakeholder. Whenever we have it in our representation, this representation is linked to other parts of the model. So in this particular case, for example, we have a link to a specification of our stakeholders. The stakeholder specification is its own little subnotation that is then recorded in the file with the extension .org. In a similar way, we can define goals or take goals from original document and associate them with immediately with a particular system. In this particular case, we are associating it with an ASSA sensor. If you want to know where that is, again, this is hyperlinked to the specification in an AADL model. And linked to stakeholders and references into stakeholder documentation that may be in ported or in document format. Requirements are specified in a similar way. Their description is slightly more elaborate. We have them defined again either in document format, or then we can optionally associate each individual requirement with an ADL model later on once we are defining it, or we can immediately define the requirements around an architectural structure. The first is a scenario that we saw animated in the slide earlier, where we have textual documentation and slowly over time are identifying architectural elements that are implicitly embedded in the requirement specification, so we can keep the original format and add with for statements references into the ADL model as it evolves. If we have already an architecture-led approach to requirement specification, then we want to already from the beginning organize requirements around architectural elements. The interest in a requirement specification for a particular system is to make them concrete enough that become verifiable, and we can indicate that by then associating with the requirements verification plans like we indicated in an earlier photo. This is done through a second notation called verify that comes with the Alisa framework. Otherwise, we have description, rationale, we have the ability to categorize requirements for later filtering for subsets of requirements to be focusing on at any point in time, and to assess the coverage as we have illustrated earlier. Relationships between requirements take several forms. One is a refinement. There the focus is on saying a requirement for a particular system, can we make it more concrete? That is, for example, if the requirement says the system shall be safe, well, what does safe mean? We can now become more concrete about it, but it is still about the one system. At the same time, once we have a system and develop a design for it into various subsystems, we now can start assigning requirements to the subsystems. This is what we then refer to as requirement decomposition. A third form is to say we have gone through a safety analysis, have identified hazard. Now we get, quote, derived requirements whose job is to mitigate the hazard. This is where we use the mitigation relationship. And we can have requirements that over time evolve and get refined or rephrased and reworded, and we have this notion of evolution. We also have added into the notation the ability to parameterize requirement specification in such a way that things that frequently change can be changed in a single place, and typically that is values, for example, what should be the maximum weight or what should be a stability point in the control function. So for that purpose, we have introduced variables that then can be used in descriptions and in formal specification of predicates, and also in verification plans. And as people make changes, they're made in one place and automatically picked up by all the relevant aspects of requirement and verification specification. We also have traceability back to goals, and with the mitigation relationship to hazards, and through the goals then back to stakeholders. We also have introduced the notion of development stakeholders, namely some requirements come from external users, but other requirements evolve as a result of a developer making architectural design decisions. So we want to be able to capture those as appropriate. And finally, we have a way of annotating the requirement specification with change uncertainty indicators, as we have illustrated in an earlier slide. Let us now look at some example system requirement specifications. First, let's look at one for the ASSA system. Again, we can identify the system that we are defining it for in the appropriate link. When we navigate to it, we find its specification. And as we see from having gone through a requirement document, we have identified a number of different interaction points where we get information from the external world into the system, and we are providing information to the external world, either other systems or the operational environment that we are dealing with. So for that purpose, then we would need to make sure that we have a requirement for each of those elements together with the behavior. At this moment, it shows us the requirements as we found them in the system requirement specification document. We have the traceability to the stakeholder and system requirement documents in the C goals reference, for example. We have a description that we inherited from the system. And as we have developed those, we have identified some issues. So at either an individual requirement level or at the collection of system requirements, we can document any kind of issue that we need to resolve and address before proceeding in the full requirement specification. Coming back to the ASA sensor as an example, we have now a requirement specification for a what's called passive terrain sensor, a sensor that provides information about terrain. Here we have introduced this concept of a variable, as I mentioned, to parameterize the requirement. So for example, we have a requirement about the spherical terrain awareness for the aircrew, and for that purpose we indicate what is the desired observation radius for that sensor. We have a variable called the desired observation radius of 5 nautical miles. Its value is then used in the description itself, as well as in a value predicate specified below here. We also have introduced a second variable with the keyword compute. This is one that brings back the result of a verification activity that performs some measurement or computation and compares it against the desired observation radius. And the value predicate is specified in one place here and is then utilized by multiple verification activities that are potentially used to verify this requirement. And in a similar form, we do that for other forms of requirements. We also can include the name of the component to which it applies in the name as well. There's a keyword list that can be used. In some cases, we want to establish the fact that the value that we have should be recorded in a property in the ADL model. And here we have done that explicitly as part of a requirement specification, where we are indicating that a value of the property of this kind associated with our component should have the value active. This is one way of establishing consistency between the values in the requirement specification and the values that are recorded in the system specification through properties. A second way of doing that is at the time we specify a verification plan, because effectively what we are doing is passing as parameters the requirement values to the verification activities. In one case, by directly passing it to the verification method being called in the verification plan, or in a second form via a property. One of the things that we can do with requirements, we actually can categorize them, and the purpose of the categorization again is to let us determine whether we have a reasonable coverage and whether we have dealt with various quality attributes. Those requirements are user definable, and we are showing you some predefined ones where we say, okay, we are dealing with implementation constraints, input assumption, output guarantees, behavior state, and so on. And in the second class, we are showing you a variety of non-functional properties of operational quality attributes with which we can characterize the requirements. That then can be used to, like I said, first make sure we have coverage, and secondly, they can be used to do focused verification activities or focused development. If our concern is, for example, around resolving issues with interplay between security and safety, we can then define filters that let us focus on just those aspects of the system. A couple of comments about the syntax for the requirement specification notation. We are showing the syntax for an individual requirement that would be placed either inside a document section or inside a system requirements section. If you have a system requirement specification, you would have identified the classifier, as I mentioned earlier. Here we can now give the individual requirement a name, typically a requirement ID. You can then elaborate through some descriptive form, through an optional title, an indicator that is then used for display purposes, for example, in navigation. In addition, you can identify a particular element inside the system, for example, a particular port that you want to have this requirement associated with. The detailed data of the requirement specification is inside square brackets. The individual fields can be specified in arbitrary order, and all the fields are optional. Category is an example where the field takes multiple values, that if you specify category, you specify one or more. Value, that's the val statement says that the whole val declaration can be repeated 0 or more times, and in similar fashion other declarations are given to you. The description field is interesting in that it takes a sequence of text and value variable references, as well as possibly the keyword this, which would fill in the name of the element to which the requirement is associated. And we have references to refines, referencing other requirements that we are refining, referencing error sources in an EMV2 specification, to identify those that are being mitigated by a particular requirement specification, and so on. And as usual, we have an issue statement where people can write down multiple issues as they encounter them, and then we have an uncertainty specification, the syntax of which I haven't shown here in detail, but it allows you to annotate uncertainty indicators as we have shown in an earlier slide. To give you a glimpse of what it looks like to use the requirement specification together with verification plans to automate your development process and verification process, we are showing you an example from a multi-tier aircraft system that was used in the Savvy initiative. The aircraft system itself is specified in a large set of projects that are shown here. Each of them contains multiple packages with system specifications at different levels of granularity. We, for these models, have then defined a set of requirement specifications. Here we are showing you the one for the flight guidance system with a number of the requirements parameterized. We then have defined verification plans. For each requirement, we have a claim that identifies what the verification activities are to be used to demonstrate that this requirement has been met. In this particular case, we have primarily one verification activity, namely a particular analysis that OSATI already supports to perform on the AADL model. We then define a configuration of the assurance plan. Then we identify the system. And in the context of that system, create and identify the verification plan. We then get an instance of this verification plan that we are executing against. It's similar to an instance model of the ADL, and when we execute it, it then goes and performs all the verification activities and maps the results back into this common structure. independent of what the particular verification technique was, whether it was a OSATI plugin, a resolute function, or some other way of verifying it, including in the future verification by running simulations of detailed design models. And so this lets you explore where we still have problems in terms of achieving the goals that we have. And in a similar way, we will be showing you metrics on the requirements. So here we are accumulating up which verification activities have been successful or failed. And again, in terms of requirements, we will have similar measures showing you where we have complete verification, requirement specification coverage, or where we need to do some additional work. In closing, we have a prototype implementation of the requirement specification as well as a verification prototype. Initially, we will release the requirement specification part, and by March, the verification element as well. The implementation, as you saw, is based on text and provides editing capabilities similar to textual AADL with context-sensitive help and content assist type of capabilities. On the verification side, we have automated running OSATI analysis plugins, resolute proofs, the ability for users to write their own verification methods that extend in Java that can be called reflectively. We are also in the middle of adding coverage and checking and other metrics, as well as improvements in the user interface to make it more user-friendly through navigation and forms-based capability. We also have a first prototype of an import-export capability with doors based on the RecIF format. Just bear in mind, the RecIF standard allows users to actually define what elements ought to be in the format, so different projects may actually have different content specifications, so there's a need for a tailored mapping from RecIF into the rec spec, and we have some initial prototype capability of that as well. Finally, 3 pointers to some documentation that give you some background on this work. 2 are the first one is the specification of the requirements language. It's a report that is currently in the review and will be available on short order with unlimited distribution. And in a similar form, we have 2 reports based on the work we have done for the shadow project of JMR. One originally published in November 2014 as a limited distribution report on the use of requirement specification and the development of the architecture model that we used in this context, and the second one to use the same setup for doing safety analysis as part of the whole process. Both of those are also currently in the review for unlimited distribution. Thank you for your attention.